while I'm talking, of course, feel free to stop me and I'll be happy to answer any questions that you have. All right. So the first question I wanted to look at, and bear with me, I can hardly read with my glasses. I need a new prescription so bad. Was question 16.31, which is really just a simple question, but we're in chapter 16 and we're going to try some of the questions. So first we're going to start with question 16.31, which asks, what is a tetrose? So a tetrose is nothing more than a carbohydrate. So a carbohydrate with a total of how many carbons? Could anybody tell me? And it's not a trick question.
4.
Absolutely, yeah. It's got 4 carbons. Now keep in mind, just because it says a tetrose doesn't mean it's a keto tetrose, and it doesn't mean it's an aldotetrose. They haven't given us that information, but we know that a tetrose is a carbohydrate that has 4 carbons. So if I take that one step further and I say, okay, well, what if I have a hexose, right? That's what question 16.32 asks us. That would be a carbohydrate with a total of 6 carbons, right? We just have 6 carbons. So you have to know the prefixes, right? You go from a triose to a tetrose to a pentose to a hexose. And of course, you could go to a heptose, but I don't think we look at any sugars that have more than 6 carbons in them. Okay, from there, I wanted to just kind of extrapolate on that a little bit and look at 16.33, which asks, what is a ketopentose? So what's a ketopentose? Well, a ketose is a carbohydrate in wherein the most highly oxidized carbon is actually part of a ketone rather than an aldehyde, right? We're all used to looking at glucose, which is an aldohexose, but if we have a ketopentose, and I'm just going to make one up here, we would have something like this, where the highest oxidized carbon at the top is actually a ketone. So we have 1, 2, 3, 4, 5 carbons like this, and then we have, hydroxyls here, and then we put hydrogens like that. So again, this functional group in here is a ketone, but we call this a ketose. And I know you all know the structure of D-glucose, and we'll probably take a look at that in a second. All right, moving on to question number, which one did I want to look at next? Was number 39. I wanted to talk to you a little bit about stereochemistry. So question 16.39, and I'm going to ask you guys, and just give me the best definition you can come up with. It asks us, what are stereoisomers? Does anybody have an idea what a stereoisomer is, or a good idea what a stereoisomer is?
Atoms that have the same arrangements
Okay.
and
Okay.
but different spatial arrangements, I mean.
Yeah. So it would be a
With this
molecules with the same arrangement of atoms, or the same connectivity, we'll say. I'll delete that and just say connectivity because I think I use that word most of the time. So with the same connectivity, right? But different arrangements, or arrangement of, and you got the key word there, atoms in space. Right? So the way that they differ is in their three-dimensional structure, right? It's in their three-dimensional structure. And we talked about what enantiomers are and diastereomers and all that kind of stuff. And so to follow up on that, could anybody tell me what a chiral carbon is? And it's not a trick question. If I have a chiral carbon, what does that mean? And you can type in the chat if you want. Go ahead.
an atom that mirrors each other with at least 4 different groups bonded.
Yeah. So since we're talking about carbon specifically, it's going to be a carbon atom, right? So, yeah, exactly. So you're both in the right vein. Yeah, Gavin says it's a carbon attached, bonded to 4 groups. But I would be even more specific. So a chiral carbon is a carbon attached to 4 different groups. Different different groups. Right, let's say we have a carbon, and attached to that carbon we have a methyl group, we have an ethyl group, we have a propyl group, and we have an isopropyl group. There we go, an isopropyl group. Right, that carbon in the middle, this is a chiral carbon because I have 4 different groups. The methyl group is a group, ethyl is a group, propyl is a group, and the isopropyl is a group. 4 different groups. It doesn't have to be 4 different atoms. That's a trap that students will fall into. Sometimes they'll say, well, it's got to be 4 different atoms. But it just has to be 4 different groups. It could be 4 different atoms, couldn't it? Right? And I showed you an example like this. What if the carbon was attached to a chlorine, a hydrogen, a methyl, right, and a fluorine? Well, that's a chiral carbon too, the carbon in the center, because it's attached to 4 different groups. A chlorine, a hydrogen, a methyl, and a fluorine are all different. And so those would represent chiral carbons. I think these examples are, and I don't like to use the word easy in chemistry class, but I would say those are easier than identifying chiral centers in, say, a carbohydrate. But we'll look at some examples of that before we get out of this chapter. So if we want to talk about question 16.45, which I think is a good question, okay, it says, what is a Fischer projection? So if I draw the structure of D-glucose, the way that it was introduced in our textbook, and you have to forgive me here, I'm doing my best drawing, I'll move this up a little bit. So this is how the structure of D-glucose was drawn in your textbook originally. Okay, like this. So this is D-glucose. Now, if I was to ask you if this is a Fischer projection, some of you might have a knee-jerk reaction and say, yeah, that's a Fischer projection. Technically, it's not a Fischer projection, right? Technically, a Fischer projection, we should leave out these carbons, right? We don't include these carbons. They're not necessary to include in a real Fischer projection. So a Fischer projection would look more like this, okay? Where we just have the lines crossing like this so that all the carbons are implied at the intersections. Okay, so then we can put in our hydroxyls like this, and then we fill in our hydrogens like this. This is actually a proper Fischer projection. I have a tough question for you. Okay, this is not, I wouldn't say this is a trivial question. Could anybody tell me in D-glucose, and these are just the same molecule, okay, but this is a real Emil Fischer projection. Could anybody tell me how many chiral carbons there are in D-glucose in the Fischer projection? It's not a trick. But I wouldn't say it's an easy question. Anybody have an idea how many chiral carbons there are? Yeah, okay, all right. Yeah, I'll do this one kind of quickly, but actually there are 4 chiral carbons in this molecule, right? We have a chiral carbon here, 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 and here. So there are 4 chiral carbons, right? The reason why these 2 carbons, this carbon is not chiral and this carbon is not chiral. Why would those not be chiral? Well, if you look at this carbon down here at the bottom, it's a CH2OH, right? Maybe I'll draw the bond the way it is, okay? Well, that carbon is attached to 2 hydrogens and a hydroxyl, right? So this carbon is not chiral. Similarly, if we draw the aldehyde at the top, you can see that the carbon is attached to an oxygen, a hydrogen, and this group down here. So it only has 3 groups bound to it. So only 3 groups bound to it. So not chiral. All right. The technical term, the proper term is achiral. That's what I started to write not achiral, but that would be a contradiction, wouldn't it? All right. So there you go. So that's a proper Fischer projection. Now, if we take this structure of D-glucose, I'm just going to copy it here quickly. Okay. Copy that. And I'm going to paste it down here. And I want to use it to draw a Haworth projection. Okay. We just leave those red and yellow dots on there. Those are not hurting anything. But I want to remind you how to draw the Haworth projection, right? We draw a 6-membered ring, right? A hexagon, and we have the oxygen in the top right corner like this. Now, if you look at your textbook, they shade in these bonds down here at the bottom to show you, to try to give you a 3-dimensional view of it. But you might remember that I told you that you have to remember that, and you have to draw this CH2OH pointing up at the top, and then you have to draw this carbon down here. So if we're going from D-glucose, and I wanted you to draw beta D-glucose, I just want to review with you the tricks that I taught you to draw the beta D-glucose, right? You count the carbons going from 1, 2, 3, 4, 5, 6, like that. And we're going to use the same numbering system here, starting with carbon number 1, which we call the anomeric carbon, 2, 3, 4, 5, 6. Now, since this is beta D-glucose, right, the beta refers to the anomeric carbon. And if it's beta, that means that the hydroxyl on the anomeric carbon is going to be pointing up, like that. So now all we have to worry about are the hydroxyl groups at carbons 2, 3, and 4, and they're all pointing to the right. And remember that anything that was pointing to the right is going to be pointing down in our Haworth projection. So at carbon 2, we're going to have a hydroxyl group pointing down. At carbon 3, we're going to have a hydrogen pointing down, which means this hydroxyl will be pointing up. And on carbon number 4, this hydroxyl group is going to be pointing down, like that. And so now we've drawn beta D-glucose in a Haworth projection. If you're the kind of person that likes to watch other videos on YouTube, you might hear that called a Haworth projection, but I grew up with Haworth projection. And my organic chemistry teacher was from South Africa, so I think his pronunciation was probably better than most. All right, give me a thumbs up if you follow me on how to get from the Fisher projection to the Haworth projection. If you hopefully took a little bit of time to practice that over the study break. Okay, good. All right, it's not meant to be a mind-boggling thing. It's more just meant to be something that you're able to do. Question number 47, I think, is sometimes a difficult question for students. When it says, what is a diastereomer? Can anybody come up with a definition or the definition that we looked at in class of what a diastereomer is? It can be very concise. What is a diastereomer? It was covered on one of the slides. So if you don't remember, I'll kind of help jog your memory on this one. Diastereomers are a pair of stereoisomers that are not enantiomers. Want me to give you an example? Yeah. Non-mirror image, non-identical. Yeah. You're in the right vein, Gavin. Absolutely. Gavin, you want me to give you the funniest, not funniest, it's not meant to be a joke, but something that will surprise my students sometimes that are in full year organic chemistry. Want me to give it the most simple example of two diastereomers? What if you have this molecule? You guys remember alkene nomenclature? All right, this would be called cis-2-butene, right? Because both of these methyl groups are on the same side. And if I was to ask everybody who's hearing the sound of my voice, if I asked all of you to go up to the board or draw trans-2-butene, I know you could all do it. You just draw this, right? You'd say, well, there you go, Mr. Young, have a nice day. There's trans-2-butene. Now, can I interconvert these two molecules? No, I can't, right? They're locked in that conformation. The cis is stuck, and so is the trans, because there's no rotation around a pi bond, right? If somebody tries to tell you, I'll just rotate that bond. Remember, we tried that in the lab with the model kit. You'd break it, okay? And so these two compounds, they're stereoisomers, aren't they? Right? They have the same connectivity. They both go CH3, CH, double bond, CH, CH3, right? They both have that same connectivity, but they're not mirror images, are they? They aren't. And so these two compounds are actually diastereomers of one another, diastereomers. Okay, so that's an example of a pair of compounds that are diastereomers. All right, it's kind of thing that we only cover sort of quickly, the whole concept of diastereomers. So I just wanted to give you an example of some compounds that are diastereomers. All right. Number 16.53, and I know that you could probably all answer this faster than me, but I just want to review a little bit about glyceraldehyde. It just asks us in question 16.53, how are D and L glyceraldehyde, how are they related? So if I have D and L glyceraldehyde, and I'll start by drawing the D, and I'll just draw the Fisher projections. It's the simplest possible aldose you can have. So this is D, glyceraldehyde, and then if we draw this, this is L, right? This is L glyceraldehyde. Could anybody tell me what the relationship is between these two? What would the relationship be between these two molecules? Does anybody have an idea? Well, these two compounds, D and L glyceraldehyde, they are mirror images. Now, the way that they're written here, you might think, well, this isn't going to overlap with this. If the mirror image, it's going to be over here, right? Well, keep in mind, these are atoms, right? Atoms are not represented by letters. Okay, so these two compounds, yes, Sadie, absolutely. They are stereoisomers, definitely, right? They both have a chiral carbon here. But not only are these compounds stereoisomers, they are enantiomers. Enantiomers. Okay? And if you're like, well, I don't like the Fisher projection, it's hard for me to tell that these are enantiomers of each other. Well, there is a plane of symmetry between the two molecules, right? You can see that the hydroxyls are reflected, the hydrogens are reflected, the aldehyde is reflected, and so is the alcohol here. That's reflected. And so these are non-superimposable mirror images, right? If I tried to take this molecule and I try to put it on top of this one, you see that it doesn't fit, does it? Right? The hydroxyls and the hydrogens don't line up. And so they are stereoisomers. You're absolutely correct, Sadie. But more correctly, they would be enantiomers, non-superimposable mirror images. Well, let me go one further. This one might require somebody to unmute their mic. Could anybody tell me how would I distinguish between enantiomers? Because enantiomers are going to have the same melting point, same boiling point, same density, right? They're going to have all the physical properties in common. All of their physical properties will be identical. Could anybody tell me how you distinguish between enantiomers?
Does it have something to do with the hydroxyl group?
Yeah, I guess so, in a way. We distinguish between. Could you extrapolate on that just a tad?
The carbon or the chiral carbon with the highest number with the hydroxyl group attached determines like if it's L or D.
Yeah, okay. So I think we're kind of talking about two different things.
Okay.
Yeah, it's okay, no problem. What I'm asking is, if you had a sample of D-glyceraldehyde and you had a sample of L-glyceraldehyde, and you mixed up the labels by accident, or the labels fell off in a windstorm, like we get in Colorado, how would you determine which one is which? You can't use a melting point, you can't use a boiling point, you can't use their density, you can't even use spectroscopy, which is something that we don't cover in this class. But if you're the kind of person who likes to watch things like Forensics Files, you might have heard of mass spectrometry or high pressure liquid chromatography or things like that. There's all kinds of techniques that organic chemists have developed to distinguish between compounds, but those techniques will not work. Hell yeah. All right. I see that somebody just wrote optical activity. Yes. C. Okay, we use optical activity. Optical activity. Right? Because each enantiomer is going to rotate plane polarized light in an equal amount, but in an opposite direction. Now, I don't have the optical rotation of DNL glyceraldehyde memorized. It's probably in the book. I don't know. Sorry, you guys. I used to study carbohydrates so much. I probably did have them memorized at one point. I thought that they might be in here. Maybe I put them in. I don't know. But let's just say, for interest's sake, and this is totally wrong. Let's say if this enantiomer rotates plain polarized light positive 10 degrees, then this one's going to rotate at negative 10 degrees. Okay, and again, I'm just throwing numbers out there. But that's how you distinguish between them, is using their optical activity. Okay, give me a thumbs up if that kind of jogs your memory and you're like, yeah, I won't forget it now. Everybody with me on that one? Optical activity, that is an important concept. Absolutely. Okay, great. You guys want to hear a quick story? It's kind of a funny one. When I was in graduate school, did I tell you about the big synthesis I did, and I was trying to determine the optical activity of a compound? Because I'm like an old person. I know I repeat myself a lot. No? Okay, well, I'll tell you very quickly, you guys. So when I was in graduate school, the project that I worked on for probably a year involved me synthesizing a natural product. So it was a compound that had been isolated from a cabbage in China. Okay, so some kind of Chinese kale. I'm not kidding. They isolated this compound and they thought it might have some anti-malarial activities. So I decided to synthesize this molecule, which again took me about a year. Now I wrote to the people in China and they sent me a sample of this compound that they got from the plant. Okay. And I knew the relative stereochemistry of all the different stereo centers or asymmetric centers or chiral centers in the molecule. I know the relative, like which ones were up and which ones were down, but I didn't know if it was the positive or the negative. So I didn't know absolutely, if I was going to synthesize the actual compound or its mirror image, right? If that makes any sense to you. And there was no way of me knowing until I did the synthesis. So basically, I had to work in the blind, like blindly, for a year and just pray that I made the right compound. And then when I measured the optical rotation, at the very end, I'd be able to tell if I had synthesized the actual compound or its mirror image. So I got to the very end and I could tell, it had the same density, it had the same melting point, it had the same boiling point, all this stuff. So everything was good. And then I got ready to do what's called X-ray crystallography, which is beyond the scope of our course, but you bombard the compound with X-rays and it gives you a three-dimensional picture of the molecule. So you know what the absolute stereochemistry is. And so I submitted it and I got it, and then I compared it to the actual, and then I measured the optical rotation. And their compound had a rotated plane polarized light negative 23 degrees. What do you think mine did? Was it positive or negative 23 degrees? Did I spend a whole year making the wrong one or the right one? Well, the answer is it was the wrong one. So I measured the optical rotation and it was the opposite. Yeah, it was the total opposite. So I synthesized the wrong one. So I had the wrong absolute stereochemistry. Again, there was no way for me to know that. But by synthesizing the wrong one, I proved what the absolute stereochemistry was of the right one. So I still published it and everybody was happy. Anyhow, it was kind of funny. After a year's worth of work, I was like, oops, guess I picked the wrong one. Anyhow, again, there was no way for me to know. I mean, I had a supervisor who's an expert, and he was like, well, we'll just go for one and see what happens. Okay. So that makes you feel like, I don't think I'm going to do research. I think I'll just stay away from that. All right, there we go. They call it research for a reason, right? Because you do it over and over and over. Okay. Question 16.61, define the term anomer. Could anybody give me like kind of a quick definition of what anomer is, or they might have an idea of what an anomer is? It's an important word. Anybody have an idea about anomers? Okay, an anomer is simply, if you compare two sugars, so let me go back and copy my Haworth projection, okay? of my beta D glucose. I'll just copy this and use it as an example. So copy. So, and I'll paste it here. And I'll paste it here again. So come on, paste. Okay. So if I simply invert the stereocenter, so I change it from up to down at the anomeric carbon, right? Remember that this is the anomeric carbon, carbon 1 of the Haworth projection. When you invert that to make the alpha, okay, the difference between the alpha and the beta, you see that every other center is the exact same. And so the relationship between these two molecules here is that they are anomers. Okay, that's what an anomer is. It's simply, now the way that your solutions manual describes it, it says anomers are isomers that differ in the arrangement of the bonds around the hemiacetal carbon. I think that's even more complicated than you need. Now you should know that this carbon, carbon number 1, the anomeric carbon, is part of a hemiacetal, right? It goes hydroxyl, and then we have an ether on this side, right? You guys know that a hemiacetal is when you have a carbon that has a hydroxyl and an ether on it. And it's got 2 other R groups. They could be hydrogens, they could be carbons. But that is a hemiacetal. Okay, so that's all anomers are. They're basically stereoisomers that differ only at the anomeric carbon. That's it. All right. So that was 16.61. Take a look at this one, 6.5. Oh, this is a good question. 16.65. I don't know if you have your textbook open or not, but 16.65 says this. I'm going to go back here and just copy my D-glucose structure. Maybe I'll delete some of my highlighting on it. It's a really good question. So if I take my D-glucose Fisher projection, and I copy this, and I paste it down here, kind of running out of space here. There we go. Why is it that when this cyclizes, it can either give me the alpha or the beta, right? I can end up with, I can end up with the alpha D-glucose. Okay, so I'll just slide it down here. I can end up with this anomer, or I can end up with this anomer. I've got either choice. Could anybody tell me why I can get both of these? Something that I went over with you, I think, kind of quickly. Right, because the anomeric carbon is this carbon. Son of a gun, I didn't mean to delete it. This is the anomeric carbon, right? That's carbon number 1. This is number 1. So this is the carbon that ends up becoming the anomeric carbon. Why is it that you can either end up with the alpha or the beta? Well, let me show you. Okay, and this is something, again, that I went over quickly. If you draw the carbohydrate out like this, you have your aldehyde here, you have a hydroxyl here, you have this CH2OH, okay? You have this hydroxyl pointing down, you have this one pointing up, and you have this one pointing down, right? This is D-glucose, not glucose, glucose, okay? So this is D-glucose molecule right here, right? This is exactly the same thing as this, right? If you number these carbons, number 1, number 2, number 3, number 4, number 5, number 6, the reaction that forms the hemiacetal is between the lone pair on the hydroxyl of carbon 5 and this carbon right here. Okay, that's what forms the bond. So this is that hydroxyl, okay, that I just showed you. And this is carbon number 1, right? This is carbon number 5 right here. So here it shows it a lot better. But remember that an aldehyde, so if I copy, now let me just delete this. If I draw the Lewis structure of the aldehyde, and you should know Lewis structures a little bit from General Chemistry 1, right? The Lewis structure of the aldehyde looks something like this. The molecular geometry of that carbon is trigonal trigonal planar, which is a polite way of saying it's flat. Okay? So what that means is that the hydroxyl can form the bond going from the top face of the molecule, or the hydroxyl can form the bond going from like the bottom face of the molecule. If it attacks it from the bottom, the hydroxyl that's formed is going to be in the beta position. And if it attacks it from the top, it's going to be pointing down. It's going to be in the alpha position. Now, look, you guys, I'm not going to ask you to draw these arrows and give me a whole big, dog and pony show about this. But I want you to understand that you're going from a carbon that is trigonal planar, totally flat, and then you're converting it into a carbon that is tetrahedral, right? These carbons are tetrahedral, the anomeric carbon, after it's formed, okay? And since the hydroxyl can form that bond coming from either face of the molecule, from either face of that aldehyde, you can end up with alpha and beta. So why don't we draw the blue arrow, and we'll say that from the blue arrow, we end up with the beta anomer, and then from the green arrow, we end up with the alpha anomer. Okay, now our book only goes into a little bit of detail about that, but I think it's important that you understand why you get alpha and beta instead of me just telling you, oh, memorize it. You get alpha and beta, and then you move on with life. All right. Let's try a question, which is, we'll try one more, and then we're going to call it a night. And then again on Wednesday, we'll do some more review. But I want to try question 16.77 with you. 16.77, which simply asks you to draw the structure of maltose. Okay, so it's kind of this. It kind of just says draw maltose, but then it gives you some information about maltose. It says that maltose is a disaccharide isolated from amylose that consists of two glucoses. So you've got a glucose, and you've got another glucose linked together. Okay, and they're linked together by an alpha 1,4 bond. So you get an alpha 1,4 bond in between them. All right. Now I'm going to add something to this question because I want to. Okay. They're just telling you to draw maltose, but remember, I told you in class that, well, you could have beta maltose and you can have alpha maltose, right? Either one. We're going to draw beta maltose just to be cheeky here. So we're going to draw beta maltose. Now, I've gone over how to draw glucose in the Haworth projection in pretty good detail this evening. So I'm going to skip a lot of that, and I'm just going to draw the molecule out. I'm just going to draw a molecule of glucose. So we have our CH2OH up here. I'm just going to put in the hydroxyls at carbons 2, 3, and 4. So I have a hydroxyl pointing down. I've got one pointing up, and I've got one pointing down. Now I'm going to draw my other glucose over here. But they're telling us that the link is alpha 1,4. It's an alpha 1,4 link. So what that means is that from carbon 1, the anomeric carbon on this carbohydrate, the bond is going to be going down. It's going to be going down, which is alpha. I'm going to have my hydroxyl. And since my hydroxyl on the next molecule of glucose, I can even copy this one and paste it in, just prove it to you. Copy. Okay. Since on the next glucose molecule, this hydroxyl here is pointing down, that means that this bond is going to go up to that hydroxyl, right? Because it's coming down. So I'm going to draw the bond up, and then I'm just going to position this so that it looks half decent for my students, like that. Okay. So now I've covered the two glucose molecules, and I've got the alpha 1,4 linkage. There you go. There's a problem with my structure. Can anybody tell me what it is? There's a fatal flaw with this that I could not give myself full points.
You're missing the hydrogens.
No, that's not a problem, because
Okay.
I can draw this. I'm just drawing it as a bond line structure, right? You can include the hydrogens if you want to, but you don't have to. If you want to, be my guest, and if not, that's fine too. Mr. Dion is Happy as long as the structure, but that's not a problem. So I wouldn't grade that wrong. Does anybody knows there's a big problem here? No, it's got nothing. Yeah, well, Sadie, good one. Okay, Sadie, you got me on that one. You burned me on that one. Okay. So Sadie's like, that's not a balanced reaction, Mr. Dion. Well, it didn't say show the synthesis of maltose. Okay, it just said draw the structure. Ah, Gavin, you found the problem. All right. So what Gavin is saying is he said, Mr. Dion, you said you were going to draw beta maltose. What I have drawn here is alpha maltose. Right? Because this symbol here, the alpha or the beta, it refers to this carbon, the one on the far right. And since that hydroxyl is pointing down, that's alpha. So I need to delete that. Okay, I'm going to delete all that, delete this, and I'm going to draw that bond pointing up. Okay, there we go. Now I've got beta maltose. Remember, and I had a student really confused on this one time. This alpha 1,4 is talking about this, right? The alpha refers to this bond pointing down. It's alpha. The 1 is this carbon and the 4 is this carbon. This beta refers to this being beta. Does that help? I hope so. All right. I hope that helps a little bit. Anyhow, because I've assigned some other problems, I think, in the book where you have to draw some disaccharides. And we also looked at lactose and we looked at sucrose. I'd never ask you to draw, but we did look at maltose and lactose. So I would expect you to be able to draw those. And just to put this bug in your ear, later on, for people that are in Group A on April 12th, and for people who are in Group B on April 19th, we're going to do a wet lab, which is the amines and amides lab, but we're also going to do a dry lab, which deals with just carbohydrates. And in that lab, you'll be asked to draw some disaccharides. So you want to be Johnny on the spot with this concept here so that you draw the correct linkages and then you draw the anomeric carbons correctly. Okay? Give me a thumbs up if that helps a little bit. Or let me know if you have a question and I'm happy to answer it.
A beta one.
Sorry, go ahead.
Sorry, if it was beta 1 through 4, then that bond right after the oxygen would be pointing down.
It would be pointing this bond. If this was beta 1,4 linked, this bond would be pointing up.
Gotcha.
The acetal bond. But the thing is that wouldn't be maltose because maltose always has this linkage.
Okay, gotcha.
Okay. All right. Well, I'll tell you what. Why don't we call it? What time is it? 12 after 6.